Hello again. In this video, we're going to begin talking about the material from section 311, which is about a very important application of the derivative known as related rates problems. So let's look at this first example. So in this first example, it says, oil rig springs a leak in calm seas and the oil spreads in a circular path around the rig. If the radius of the oil patch increases at a rate of 30 meters per hour, how fast is the area of the patch increasing when the patch has a radius of 100 meters? Okay, so this is the point at which the oil leak begins. And the oil leak spreads in a circular fashion. The rate at which the radius of that circular oil leak is increasing is at 30 meters per hour. What they want to know is how fast is the area of the patch increasing when the patch has a radius of exactly 100 meters. Okay, so let me show you how to work this out. So this is a related rates problem. When you have a related rates problem, what you should probably do first is write down all the rates of change that you're given and all the rates of change that you're trying to find. And so in this case, they told us the rate of change in the radius over time was 30 meters every hour. So that's really a derivative. It's the instantaneous rate of change in the radius over time. And so it's just the derivative of r with respect to t. In other words, dr dt. So that's equal to 30 meters per hour. And by the way, that's a constant number. Regardless of what time you're looking at, this is the rate of change in the radius over time. Now, the rate of change they want us to find is the rate of change in the area over time. Right when the radius is 100 meters. So we're going to evaluate, in other words, the derivative of the area with respect to time, dA dt, evaluated at this moment in time when r is equal to 100 meters. The radius is equal to 100. Okay, so the reason this is called a related rates problem is because we have different rates of change, dr dt and dA dt. We need to relate them somehow in an equation. The way we're going to do that is we're going to start off with what I think of as the fundamental equation or the foundational equation. In this case, it's the area of a circle. The area of a circle is pi r squared. And then from this equation, this foundational equation, we're going to create these rates of change. And the way we're going to do that is we're going to take the derivative of this equation with respect to time on both sides, since these rates of change are with respect to time themselves. Okay, so let's do that. Let's take the derivative of both sides with respect to time. Okay, so on the left-hand side, that's just dA dt, which is what we're looking for. And on the right-hand side, pi is a constant, so you can take that outside the derivative operator. Then notice that you're left with the derivative of r squared with respect to time. The radius does depend on time. It's a function of time. The problem is we don't have an equation which actually gives us the explicit radius as a function of time. So we don't know what this equation is equal to. We do know that the radius does depend on time, so we can find the derivative of it with respect to time. We have to use the chain rule. And that's because r is the inner function, and it's being squared, which is the outer function. And anytime you take the derivative of a composition of two functions, you have to use the chain rule. Okay, so using the chain rule, the outer derivative is just going to be 2r to the first, right? The 2 comes down and you subtract 1. And then you take the derivative of the inside function, which is r, with respect to time. So that's your inner derivative. And this one's your outer derivative. Okay, so this is the derivative of r squared with respect to time, using the chain rule. Okay, so we get 2r dr dt, and then that's multiplied by the constant pi. And that's equal to dA dt, which is what we're trying to find, except we want to evaluate this derivative right when r is equal to 100. So we're going to evaluate this when r is equal to 100. So let's rewrite this. In other words, we're going to plug 100 in for r here. And then dr dt, remember, is a constant. It's equal to 30 meters per hour. And I guess this is in meters because it's a radius. Okay, and so multiply that by the 30 meters per hour. And then you just have to multiply these together. Now notice the units here, you're going to get meters squared per hour, which matches the derivative here, because area is measured in meters squared, and then time is being measured in hours. Okay, so then you just multiply those together. And if you do this on a calculator, you get 18,849.56. And this is rounded to the nearest hundredth. Okay, so what does this say? What does this mean? So basically what this is telling us is that the area is increasing at a rate of about 18,849.56 square meters every hour, right when the radius of the circle is 100, at 100 meters. Okay, so I hope you found this video helpful. Thank you for watching.